In question number 11, a conical pendulum of length L is equal to root 3 meter is rotated with angular velocity omega is equal to root 20 by 3 radian per second as shown in the figure. At what angular speed should it be rotated so that semi-apex angle gets double? So let's first understand the first situation. This is the bob of the pendulum. So mg is acting in this direction, tension T is acting in this direction. If this angle is theta, then the angle from the vertical is theta. So the component of force in this direction is T cos theta, and in this direction is T sin theta. So I can write T sin theta is equal to m into omega square into L. So if this is L cos theta, and then this will be L sin theta into L sin theta. So if I balance the forces in vertical direction, then I can write T cos theta is equal to mg. So substituting the value of T, that is mg by cos theta, is equal to m omega square L. So m gets cancelled out. So from here we get the value of omega, that comes out to be under root g by L into cos theta. So this is the relationship. So if I calculate the value of cos theta initially, then it is equal to g by omega square L. So let's substitute the data. G is 10, omega value is 20 by 3, under root of 20 by 3. So on squaring this, it comes out to be 20, here it is 3, and the value of L is root 3. So on solving this, it comes out to be root 3 by 2. So the value of theta initially is 30 degree. So let the angular speed is omega 2, then I can say that omega 2 by omega 1 whole square is equal to cos 30 degree divided by cos 60 degree. Now the angle becomes twice. So from here I get the value of this, and this is equal to cos 30 degree is root 3 by 2 divided by cos 60 degree is 1 by 2. So from here the value of omega 2 is equal to omega 1 into 3 raised to the power 1 by 4. Now we have to calculate at what angular speed. So let's substitute the value of omega 1. So the value of omega 1 is under root 20 divided by under root 3, and here it is 3 raised to the power 1 by 4. So if I solve this, it comes out to be under root 20 divided by 3 raised to the power 1 by 4. So option 1 is the correct answer. So the correct answer for question number 11 is option 1. Let's move to question number 12. In question number 12, 6 particles are at the vertices of a regular hexagon of side length L. They start moving with constant speed in such a way that each particle always aims at next particle in same sequence. The distance covered by each particle till they meet is. So let's understand the situation. Suppose these are the 6 particles moving in a regular hexagon, and at any moment that this particle is moving with the speed v in this direction, and this particle is chasing toward this particle with the speed v. So at the moment, if I calculate this angle by the geometry, it comes out to be 60 degree. So if I calculate the velocity of approach between any two particles, it comes out to be v minus v cos 60 degree, that is half, and it is equal to v by 2. So the relative separation between the two particles at this moment is L. So if the time taken to meet these two particles is t, if the time taken by the velocity of approach to meet the particle is t, then I can say that v relative into t is equal to L. So let's substitute the value of v relative, that is v by 2 into t, or I can write vt is equal to 2 into L. So if v is the velocity of the particle and t is the time taken by the particle to meet the other particle, then the distance covered by the particle in time t is vt, and this is equal to 2L. So option 2 is the correct answer. So the correct answer for question number 12 is option 2. Let's move to question number 13. In question number 13, a block of mass m is suspended with two ideal springs of a spring constant 2k and 3k as shown in the figure. The block is released from rest when springs are in their natural length. The maximum elongation in spring 1 will be. So let at t equal to 0, these two springs are relaxed and block of mass m is attached. So if I release the block of mass m and let the maximum displacement of this block from this position is x max. So during this motion, when the block reaches to this position, let the extension in spring 1 is x1 and the extension in spring 2 is x2. Then I can say that x1 plus x2 must be equal to x maximum. So at that moment, if I equate the spring forces at this point, so I can write 2k into x1 is equal to 3k into x2. So from here I get the value of x2, that is equal to 2x1 by 3. So if I substitute the value of x2 here, I get 5x1 by 3 is equal to x max. Now if I apply the work energy theorem for these two positions, then I can write work done by all the forces is equal to kinetic energy final minus kinetic energy initial. So the kinetic energy at this moment initially is 0, and at this moment also, when the block has descended maximum distance, the final velocity is also 0. So I can write the work done of gravitational force and the work done by springs. So the work done by gravitational force is mg into x max minus work done by spring 1 is half into k, that is 2k, into x1 square, that is the negative work done, minus work done by spring 2 is half into 3k into x2 square, and that is equal to 0 minus 0. So if I substitute the value of x2 is equal to 2x1 by 3 and x maximum is equal to 5x1 by 3, I will get the value of x1 and it comes out to be 0 and mg by k. So the maximum elongation in spring 1 is mg by k. So option 1 is the correct answer. So the correct answer for question number 13 is option 1. Let's move to question number 14. In question number 14, a uniform rope of mass m is suspended by fixing its two ends with valves as shown in figure. Tension in the rope at lowest point P. So this is the lowest point. So if I draw the free body diagram of the rope, so let tension T1 is acting in this direction and this angle is 30 degree. So the component here is T1 cos 30 degree and the component in this direction is T1 sin 30 degree. So if I take the tension at this point is T2, then this angle is 60 degree. So this angle is 60 degree. So the component in this direction is T2 cos 60 degree, as I have taken this force as T2, and in this direction is T2 sin 60 degree. Suppose if I break this rope at the lowest point, then I can say that the situation is something like this. Suppose this is the rope. So if I consider the forces in horizontal direction on this rope, then T1 sin 30 degree is acting in this direction and tension at point P is acting in this direction. So I can write tension at point P is equal to T1 sin 30 degree. In the similar fashion, if I see the other part of the rope, it is equal to T2 sin 60 degree. So this is my first equation. Similarly, if I write the forces in vertical direction, then T1 cos 30 degree plus T2 cos 60 degree is equal to mg. This is my equation 2. So if I solve the equation 1 and 2, then from here I will get the value of T1, and T1 comes out to be root 3 mg by 2. So we have to calculate the tension at the lowest point P. So the tension at lowest point P is T1, that is root 3 by 2 mg into sin 30 degree, that is half. So it comes out to be root 3 by 4 mg. So option 3 is correct. So the correct answer for question number 14 is option 3. Let's move to question number 15. In question number 15, a uniform rod of mass m and length L is held horizontal as shown in figure. The coefficient of friction between the light ring and the rod is mu. The work done by external agent to slide the ring slowly from x equal to L by 2 to x equal to L is. So at t equal to 0, the normal reaction by the ring on the rod and the mg passes through the same line of action. So at that moment, they are in equilibrium. So at that moment, the rod is in equilibrium. Let at any time t, when the ring reaches to this position and it is at a distance x from here, at that moment if I draw the free body diagram, normal reaction is acting in this direction on the ring, external force is acting in this direction, and since the ring is sliding slowly, friction force is acting in this direction, and the friction is limiting friction. So I can say that the value of external force is equal to the limiting friction at that moment, and it is equal to mu into n. So now I have to calculate the value of the normal reaction at this moment. Since the rod is horizontal, so I have to write the torque equation about this point, and on writing the torque equation, n into x must be balanced by the torque due to gravitational force, that is equal to mg into L by 2. So from here the value of n comes out to be mgl divided by 2 into x. Suppose the ring moves from this position to this position in time dt, and this displacement is dx. So the work done by the external agent in shifting the ring in time dt will be dw is equal to f into dx, and the net work done is equal to integration of dw, and the variable x varies from L by 2 to m. So this is equal to mu into normal reaction, that is mgl by 2. In the integration it is dx by x. X varies from L by 2 to L. So further w comes out to be mu into mgl by 2 into ln 2. So option 3 is the correct answer. So the correct answer for question number 15 is option 3. Let's move to question number 16.